In this video, I'm going to go over the basics of analyzing RLC circuits. As with RC and RL circuits, we can think of two basic configurations. One is in parallel, and the other is in series. For both of these circuits, we are going to assume that the inductors and capacitors hold certain amount of energy initially, and we are going to see how they dissipate that energy as time passes. So we are going to measure voltage in the case of parallel circuit, and we are going to measure current in the case of series circuit. The equations we are going to exploit are these four equations. These two equations describe the characteristic of a capacitor, and these two equations describe the characteristics of an inductor. Now, if you're not familiar with where this equation comes from, you can watch my previous video, the introduction to capacitors and inductors. So let's look at the parallel version first. So according to KCL, if we apply KCL on this node right here, the current flowing out of this node should equal to 0. So this equation is always true. And if we rewrite this equation in terms of voltage using this equation, the equation can be rewritten in this form. I try to write this in terms of voltage because we are trying to find the voltage across these 2 points. Now this equation looks quite complicated because we have integral and we have derivative. So we are going to differentiate both sides of the equation, and the equation can be rewritten in this way. So it comes down to this question: how do we solve this equation? Now this is a second order differential equation, and there are many approaches to solving this problem. The simplest way to solve this problem is to assume that our solution v of t comes in this form, and this k and s is constant that we have to find. Now you may be wondering why we use the exponential function. This is because when you differentiate the exponential function, you get its own self times constant. So we were trying to exploit this characteristic. Now I'm not going to go over the very details of how to solve second order differential equation in this chapter. I'm going to explain it in another video. So let's plug this v of t to this equation and see where it leads us. This is the equation that we get, and we can rewrite this equation in this form. Now we all know that this cannot be 0. So in order for this equation to be true, this part has to be 0. And as we all know, there are two solutions for S. This means that our actual solution should look like this. And I used plus sign because of the linearity of the solution. Wait, what is linearity? If we assume that V1 satisfies this equation, we can write this equation. And if we say that V2 also satisfies this equation, we can also write this equation. And if we add these two equations up, we can come up with this equation. And from this equation, we can see that if V1 and V2 is the solution to this problem, we can see that also V1 plus V2 is also a solution to this problem. And this is called the linearity of a solution. So using this property, we can find that our v of t can be written in this form. Now you may be asking, why use this solution when this solution looks much more simpler? And this is because we have two initial conditions in this case. If we have two initial conditions and we have one variable, we are never going to satisfy this equation. Since we have two initial conditions that we have to satisfy, we need two variables. So we cannot use this as our solution. One important thing to note is that this equation is called characteristic equation. If you write this more nicely, it looks like this. And we all know that this is a general form of quadratic equation, and the number of solutions is dependent on the discriminant. If this value is bigger than 0, we are going to have two solutions, two real roots, and if this is 0, we are going to have one root, and if this is less than 0, we are going to have two imaginary roots. And the response of RLC circuit is different for these three cases, and we are going to look over them now. Now before we proceed, we are going to define some new terms. Now this alpha is called network frequency, and it tells us the attenuation of a circuit's response. It tells us how fast a circuit's response decays when there is no signal anymore. This omega 0 is called resonance frequency, and it is sometimes referred to as undamped natural frequency. It tells us the frequency of which this value, voltage or current, is at its highest. And finally, this value is called damping ratio. And we are going to go over this in a moment. So if we rewrite the solution to this characteristic equation in terms of alpha and omega 0, we can write this in this way. And if you look at this part, the discriminant, according to this part, the nature of the solution changes. And we are going to look at each cases. Our first case is when alpha is greater than omega 0. Now for this case, we have two real roots, so the answer comes in this form. Now in most cases, when you're trying to solve a problem related to this case, you will be given two initial conditions. The first one is v of 0, and the second one is the derivative of v of 0. In this case, you first need to solve the characteristic equation and find the value of S1 and S2. And from these two initial conditions, you can find the value of K1 and K2. Now, the second possible case is when alpha has the same value as omega 0. In this case, since S1 and S2 is same, we are going to have a form of solution that look like this. But there's a problem with this equation because we have two initial conditions that we have to satisfy. And we can assume that our solution is some form other than this form. And our solution in this case actually comes in this form. Now you can see here that there's a t added in this equation. Now I found this using the differential equation theory, but I'm not going to go into the very details of it in this chapter. So as you did with the first case, all you need to do is to use the characteristic equation along with the two initial conditions to find the value of K1 and K2 and S. The third case is when alpha is smaller than omega 0. Now in this case, we are going to have a complex conjugate that looks like this. And we are going to define a new term called omega d, which has this value. Now this omega d is called damped resonant frequency. And if we rewrite this equation using omega d, the equation that we get comes in this form. And if we separate the complex exponential part, it looks like this. And we are going to replace this complex exponential part using Euler's formula. I'm going to skip the calculations, and our final answer comes in this form, where A1 equals K1 plus K2, and A2 equals J times K1 minus K2. And just like we did with these two cases, when you are trying to solve a problem, all you need to do is to use the characteristic equation and find the value of omega d, and then use the two initial conditions to find the value of A1 and A2. And if you see here, damping ratio tells us the nature of our response. This case is when zeta, the damping ratio, is bigger than 1, and this case is when zeta is equal to 1, and this is when zeta is smaller than 1. This picture summarizes what we have learned in this video. Now I'm not going to go over how to solve series circuits because it goes through the same process as solving the parallel circuits. The only difference is we use KVL equation instead of KCL equation. The equations on the left are the equations for the parallel circuit, and the equations on the right are the equations for series circuits. And our solution is divided into three cases dependent upon the value of damping ratio. If it's bigger than 1, we are going to have to use this equation. And if it's smaller than 1, we are going to have to use this equation. And if it's equal to 1, we are going to use this formula. And of course, this v of t changes to I of t in this case because we are trying to find the value of current in this case. And if you compare both sides, the only thing that changes is the Neper frequency and the characteristic equation. The resonance frequency, the damping ratio, and the solution stays the same. The last thing I'm going to do in this video is to describe the response of these three cases graphically, which is divided according to the damping ratio. The first case is when damping ratio is greater than 1. In this case, we have two exponentials. And since S1 and S2 has a negative value, the graph would look something like this. It will be a simple decaying graph. Now the second case is when damping ratio is equal to 1. If you see here, we have t added to the original equation. And because of this t, our v of t would increase initially, but because of the exponential factor, it will start to decay again, just like the previous one. Our third case is when zeta is less than 1. Now, if you look at this equation, we not only have the exponential factor, but we also have sinusoidal components. When you draw the graph, it will be a decaying graph, just like the previous ones. But because of the sinusoidal components, our graph will oscillate within this range. So this is what our graph will look like. So as you can see here, the response of RLC circuit is quite different according to the damping ratio. And you could also see that solving RLC circuits in this way can be quite difficult. There are many other ways, such as using Laplace transform, and we are going to go over those things as we solve examples.